Okay, so let's sort of do a couple of problems, right, and see if we understand what we've been, trying to learn. Okay, so let's take this problem. Okay, so say the thrust equation for a rocket engine. Okay, so we have a rocket engine, okay, and I'm going to write the thrust equation for that. So this is thrust, right? Okay, so this is given. So the thrust that is going to be generated by the rocket engine is given by this equation. Okay, so here this is the mass flow rate. Okay, m dot. This is UE. Okay, which is the exit gas velocity. This pressure is the exit. E is for exit. Now pressure. Okay, P infinity is the ambient atmospheric pressure, okay, free stream pressure, and AE is the area of the nozzle at the exit. Okay, so given that, so we have a liquid hydrogen and oxygen which are burnt in a combustion chamber, producing a combustion gas pressure. Okay, so in the combustion chamber, okay, so like I said, so liquid hydrogen and oxygen are burnt in the combustion chamber, which results in a pressure of 30 atmospheres and a temperature of this. Okay. Now, regarding the nozzle, some other parameters, some other values are given, right. So, if you remember, so AT here, this is the area at the throat. So, this is given, okay, this is given as 0.4 meters square, right. Pressure at the exit is essentially the ambient pressure, which is equal to that the universal gas constant is given joules per kg Kelvin. Okay. So, this is the parameters which are given. So, the coefficient of specific heats is given as 1.22, okay, gamma that is, and assume isentropic flow. Okay, as the gas expands, so you basically have isentropic flow. Okay, and what we have to find out here is area at the exit here. So, what we need to find out is calculate this area at the exit and the total thrust. Area at the exit and the total thrust. So, these are the two things that we need to calculate here. Okay. So, in order to do that, what we can see here, first things first, that we need m dot, we need m dot, we need u dot. Okay. So, let us go ahead and proceed to calculate this. Okay. Let us go ahead, how will we sort of go about this. Okay. Now, so let us start with the continuity equation. Okay. So, continuity equation tells us what? So, from continuity, okay, so right. So, what would be a convenient place to take the to consider this mass flow rate? Let's say, let's take the throat, okay, as a convenient location. And if you remember right, so we all the values at the throat of the nozzle is regarded with the superscript star. So, we will do that here, okay. So, let's say, so therefore, taking it at the throat, right, at the throat, a convenient location. So, what we get is okay. Now, to get this rho star, okay, to get this rho star, okay. Now, let us get the reservoir density, right, which I can basically get for my gas equation, right. So, so this is my the knot here corresponds to reservoir conditions, okay, which here how do we calculate this rho naught, how do we get this out here? Is there anything here you think we should be able to use in this particular case? If I have to use if I have to find out the reservoir density, right. So, that is the density which we can in this here when we say that in the combustion chamber, okay, two gases are burnt which results in these. So, this is essentially the reservoir conditions. So, we can consider essentially this P and this T are the reservoir conditions, and R is given to us. R is given to us here. Okay. So, we will use that. So, P naught. Okay. Now, 30 atmospheres and 1 atmosphere is how much? If you remember right. So, 1/8, yeah, 1 atmosphere is okay, in Newton per meter square. So, we have got P naught and we got T naught and we got R. So, it is in Kelvin, so that can remain in Kelvin. Okay. So, if I do that, so essentially I can write this as okay. So, this is the pressure in Newton per meter square, this is the universal gas constant and this is the temperature in the combustion chamber, and we get this to be okay. You should just cross check this, you should just do it and use your calculators to cross check that I have got this correct, you know, I might be wrong. So, make sure I have got these calculations right. Okay. All right. So, I get the density of the gas, right, gas sort of mixture in the combustion chamber. Out here we were given just pressure and temperature. So, now we have calculated the density. This is my reservoir conditions, right, in the combustion chamber, which I have got as 1.665. So, why do not we write that here also, okay, since we have calculated this. So, since we have calculated values, let me write that here. Okay. So, this is a calculated value. Okay. Now, then how do we get the density at the throat? So, okay. Now, what we will use here, if you remember, for a calorically perfect gas, right, for a calorically perfect gas, right, this is an equation which holds, okay. This is an equation which holds for a calorically perfect gas. Now, rho naught is something that we have calculated. Now, let us take rho star. If I take rho star, okay, so if I consider rho star, which is at the throat, right, so I basically get m star, which is equal to 1. So, basically throat is the sonic zone, right. So, this goes to 1. So, we are left with this expression here, right. So, therefore, if I calculate this, okay, so what I get out here, then I put gamma is equal to 1.22, right, and what I am able to get is this rho star is this, okay, and I calculate that to be so I get the density, okay, I get the density at the throat to be 0.6 times the density in the combustion chamber, which comes out to be this, okay. You should cross check this, just put in 1.22 here and calculate this using your calculators or whatever, and make sure I've got these values right, okay. So, this is the density in the so density is done. So, what we get over here is this is now done, okay. So, what we get, this is 1.036, okay, rho star, okay. Now, having done that, now the next thing is we will go ahead and calculate this u star, okay. We will calculate u star. So, how do we do that, okay. Now, at the throat, which is sonic zone, m star or Mach number is 1, okay. So, at the throat, okay. So, therefore, u star is equal to a star, right, it is equal to the speed of sound, right. So, which is again speed of sound is again equal to gamma r t, okay, gamma r t, and here because it is at the throat I can write this as t square. T star, and again gamma and r are constants which are known. I need to find out T star, okay. So, if you are already not guessed, we will again use the equation for a calorically perfect gas like we use for the density, and the corresponding relationship is this, right, if you remember correctly. Okay, this is the relationship of the reservoir conditions and temperature. Okay, reservoir conditions of and the temperature anywhere in the flow in the nozzle. So, in this case, if I put this as T star, then this goes to 1, right, if I do that. So, once I do that, so therefore, I can write basically T star, okay, comes out to be so the temperature at the throat comes out to be 3154 Kelvin, and if you remember the combustion chamber, it is 3500 Kelvin. This is around 3160. Okay. So, temperature, having got that, so therefore, now we can get U star, isn't it? So, therefore, we get now U star, okay, U star. So, therefore, we get that as 1.22 right, and this comes out to be okay. So, U star comes out to be 1415 meter per second. Okay. This is what we get here. Okay. So, therefore, so what we know over here? So, we have M star, so rho star and U star. So, we have got U star now. Okay. We have got the velocity as well, which is 1415 meter per second. Okay. I still need A star. okay, A star, which is the here. Now, A of the throat is actually given to us, okay, area of the throat is given to us. So, this is nothing but A star, this A is nothing but A star, okay. So, which is given to us as 0.4, okay, this is given, which is 0.4. So, if I do that, then what I get as m star is essentially 586.4 kgs per second. Okay. So, basically we get this, this is the mass flow rate. Okay. So, we get a mass flow rate of 586.4 kg per second. Okay. So, having got that, now the next thing we definitely need is the, so this is something that we've got. Okay. Now, let us look how we can calculate the velocity at the exit, UE at the exit. How do we go about doing that, right? Now, so let us try and find out the Mach number at the exit. We have no clue as to what that is, right? And then we will see, because if you see here, we have relationships between the densities and Mach number, okay, change in density and Mach number, change in temperature and Mach number. So, maybe we will go and use this sort of thing, okay. If you look here, let us try to see what we can use. So, now what we know here is the reservoir pressure. If you look here from the information that is available to us, we have the reservoir pressure here, which is P naught, and we also know the reservoir pressure at the exit, okay, which is this, right. Now, these two should therefore give us a relationship of with the exit Mach number, because yes, so like we have density relationship, we also know that we have right. So, we have this relationship of the stagnation pressure and pressure anywhere in the nozzle with the Mach number. So, here if I consider this as an exit, this is the corresponding exit Mach number. So, I am going to use this and find out the corresponding Mach number. Okay. So, and this is given, this is given to us, this is something, this is also actually given to us, P naught is also something that is given to us. Okay. So, using that, okay, using here, so I will just write down the values over here, right. So, what is the sort of relationship that we get here? So, P naught is essentially, right, this is given, then this is PE, okay, this is equal to 1 plus, this is also given, okay. So, from here I can calculate the exit Mach number. So, I get the exit Mach number to be so, I have an exit Mach number just over 4. Okay. So, having done this, therefore, how do we calculate the now at the exit Mach, we have an exit Mach number, we do not have the exit speed of sound. Okay. So, let us do that. So, therefore, now UE is of course ME into speed of sound at the exit, and we do not have that. Okay. Now, let us do this again. Basically, we can write again, you know, this we can write as gamma r T at the. So, I can write the speed of sound at the exit in terms of this, in terms of the temperature. Now again, the temperature at the exit is something that I haven't calculated yet. Let us see if I can do that. I'm going to again use this equation here. Okay, last time we put the throat, instead this time we will put this as the exit. Okay, so therefore, so basically I have T is equal to, right. So in this case we have this as the exit, we have this as the exit, and by now we have calculated the Mach number as 4.38. Okay, so we've calculated this. Okay, and T naught, which is the ambient the reservoir conditions, this is 3500. Right. Having known that, we can now calculate TE from here. Okay. So TE from here therefore comes out to be, TE from here comes out to be this, right, and hence corresponding AE, okay, and hence this comes out to be corresponding speed of sound comes out to be 1.22520, right. This comes out to be 844.8. Okay, it is nearly 845 meters per second. So this is the speed of sound at the exit. Okay, so once having found that out, we'll go back and put it in here. So what we get here is basically this is right, and this comes out to be it's nearly 4,000 meters per second. It's 3,700 meters per second. So the velocity at the exit is 3,700 meters per second. Let's go and look here. So what do we have here? Okay. So did we find out the mass flux? Yeah, we did. So this mass flux is 586.4. It is 586.4 kg per second, right? And the velocity at the exit is 3,700 meters per second. That's a pretty high speed, don't you think? Okay, and of course, if you look here, that's all I need to calculate the thrust, because the pressure at the exit is equal to the ambient pressure which is given to us. So therefore, this term will anyway go to 0 out here. Okay. If not, then of course, if something else is given, then we will probably use this. But nevertheless, we still want to calculate the area at the exit. We will do that. Okay. So anyway, we are done with the thrust though. So thrust comes out to be, let's write out the thrust first. Okay. So thrust comes out to be around 2.2 or 22 kilonewtons actually. Yeah? 2170 actually. It's 2170 kilonewtons if you were to look at this. So this I can write as just to give you a little more idea. So basically what we have here is we have nearly 2,200 kilonewton thrust being generated by the rocket engine. Okay, this is the total thrust. Okay, so now let us look at what would be, so area at the throat is 0.4 meters squared. Okay, now what is the area in the exit? Okay, so let's go and see how we will do that. Okay, so in order to do that, Okay, so yes, so now again using the continuity between the so at any point, if I say at the throat conditions, right. So, mass flow rate at any through any portion of the nozzle is equal to that through the throat, right. So, from this I can write this equation as, right, this is equal to okay. So, now then I am going to write this. Okay. Now, basically I am going to introduce the reservoir conditions here, right, because we have already calculated rho star by rho naught, etc. Okay. So, let me write it. So, therefore, I can write this, okay, square this and write it like this. Okay. Now, this u star, okay, u star is velocity at the throat. So, which is again equal to the speed of sound, because Mach is 1. Okay. So, then I can write this as a star by u, okay, square. Okay. So, if I'm able to write it like this, okay, now if you remember right now, this rho star by rho naught is essentially cross check this. So, we had just written out the relationship between the relationships between the densities with Mach number. So, if you write here with respect to the throat, the Mach number goes to 1, and this is the relationship. So, rho star by rho naught is something which is available here. Okay. So, and this, and of course, this is the relationship right. So, we will get a value for this. So, we can write that it's a finite value from here. Now, rho naught by rho will be in terms of the Mach number. It will be in terms of the Mach number. So, we can get that in there. Okay. And again, a star by u, right. So, this is what? This is nothing but, so velocity by velocity of sound at the throat, right. So, this is nothing. Okay. So, essentially velocity by velocity at the throat, velocity of speed of sound at the throat, this is nothing but, okay, right, and this I can also write in terms of so this is gamma plus 1 by 2, right. This is the, so this is, then you connect that with the Mach number. Okay. So, this is the relationship that we have. So, if you look here for this particular this particular expression here, so A by A star, okay, A by A star. So, if you look at this, okay, so what we will have here is that this is a finite value which you get from here. Now, this is a term which we can write in terms of the Mach number here. Again, this is something we will write in terms of the Mach number over here, Mach number over here, right. So, if I do that, okay, so I will get an expression for this in terms of the Mach number. So, let me write that out. So, if I write that out, it comes out to be this. Right. So, basically what we have here is what we have done here. If you look at this, okay, if you look at this, that we have connected the area at the throat with the area and Mach number anywhere in the nozzle. Okay, that's what we have done. If you see, this is the area at the throat which is given to us, and this is area anywhere in the nozzle, and the corresponding Mach number at that point, where at the location where we are considering this area, and the gamma is known to us. So, in this case, of course, we need the area at the exit, right, and we have calculated the Mach number at the exit. So, therefore, in this particular case, if I had to write this, so basically what I need is area at the exit, right. So, then this becomes Mach number at the exit, and Mach number at the exit is something that we have calculated, right. So, here 4.38. So, essentially this value is known to us now, this is given to us. So, what we get as if I calculate this, so AE therefore, so A at the exit, right. Now, A at the exit comes out to be a little more than 40 times the area at the so area at the exit, okay. So, area at the exit here comes out to be right. So, therefore, now we have calculated the area at the exit, right, and this comes out to be nearly actually little more than 40% of the area at the throat, right. So, let us just take a step back and see what is happening here. So, we have a rocket engine, okay, rocket engine. So, we have a a diverging nozzle where the area at the throat, okay, where the area of the exit is nearly 40 times or a little more than 40 times the area at the throat, right. So, we have this diverging nozzle. So, the combustion chamber pressure, temperature, etc. is given, okay. So, we have an isentropic expansion of the flow over here, okay. So, at the exit, okay, did we calculate, yes, we have calculated, I think, right. So, at the exit, okay, the temperature is 1125. So, at the exit, okay, at the exit, so let me just sort of write this down. This is the interesting part here. Okay. So, okay, so now I have this, say, diverging nozzle. So, this is the area at the throat, this is the throat region, and this area, okay, area at the exit, it is this area at the exit is actually nearly 40 times the area at the area of the throat, okay. That is how it is expanding. So, then and the combustion chamber, okay, combustion chamber pressure, temperature, combustion chamber pressure is 30 atmospheres, okay, and temperature is 3500 Kelvin. The temperature at the exit drops, right, to a little over 1000 Kelvin. Okay. So, combustion chamber, the pressure, the temperature generated in the when the gas is produced, it is produced at 3500 Kelvin. Due to the expansion at the exit, it drops down to nearly a little over 1000 Kelvin. Okay. So, right. Okay. So, and this when I am able to do this, so I generate a thrust, okay, which is nearly 2,200 kilonewtons of thrust is generated when I have a rocket, a diverging nozzle like this. Okay. So, okay, so that was basically how we would use a differential area nozzle to generate thrust. Okay. So, and the connection of area, the change in area with the Mach number, and hence the velocity. Okay. So, okay, so that is one problem. So, let us now go ahead and try another problem. Okay. So, this is, like I said, this is the flow properties connected with the area. Okay. And the important thing to note here is that the area, okay, the area change, okay, can be related to the corresponding Mach number, and hence it can be related to the pressure, temperature, density changes as well, which is what we just did over here. Okay, so I guess we won't be able to finish the next problem, but we'll start it nevertheless. Okay, we'll start this and see see some interesting things from there as well. Okay, this is also a very interesting problem, and I thought that it would be interesting to sort of understand this. So we have done, right? We have done basically normal shocks, oblique shocks. Okay. And we've also done shock interactions and so on and so forth. Okay. So, okay. So, now here what we have is basically we have a supersonic flow, okay, which has a Mach number 3, okay, and we want to basically, the simple thing is we have a Mach 3 flow and we want to slow it down to subsonic speeds, that is all. So, we have a supersonic flow . Right, which is of, right, we want to slow this down to subsonic speeds. Right, we want to slow this down to subsonic speeds. Okay. Now, I mean, what do you think we should do? I mean, just stop it, turn the flow into itself. So maybe just if I want to do that, I'll go through a shock. What we will do, however, is look at this in two separate ways. So apparently we could do this less or more efficiently. We'll see how. Okay. So let us try these two cases. Okay. One is we will pass this directly through a normal shock wave. Okay. So we will pass this through a normal shock wave. Okay. And the second is first pass this through an oblique shock wave and then a normal shock wave. Okay. So first in this case, first it goes through an oblique shock, right, where the shock wave angle is given as 40 degrees, and next is through a normal shock wave. Okay. So we will see whether these will be different. Okay. So, and if these are different at all, which one should I choose? Well, should I choose this or should I choose this? And of course, why, right? So, in order to do that, so also another thing is, so calculate, okay, I think you know, this kind of, the answer kind of lies in the question. To if these two are going to result in different, if these two are going to give us different results, and how are we going to then choose which one should we go about, you know, using in order to do this? And the answer kind of lies in the question itself, but I'll write it down anyways. So calculate the ratio of the final total pressure values for the two cases. So basically in this case, so we can say the so what we need to calculate here is the ratio of the total pressure values for the two cases and the significance of that. Well, the significance of that itself is actually going to give us clues as to which one we will need to choose in order to do something like this. Okay, so so what we will do here is go ahead and just do the problem first, which by this time you should be, you know, it should not be a problem. But what we'll look at is that, you know, the physical aspect of it. Okay. Okay. So let us do this. So first things first, let's go ahead and you know, we will do this normal shock wave. Okay. So if we look at this, so we have basically so this is our normal shock. Okay, and okay, so let's call this as okay, total pressures here, and this is this. Okay, so now so this is basically for, we just passing the flow through a normal shock wave. Okay, if I do that now, from if I now start using the tables, right, if you go and look at the tables, so from the tables what we get is that right, is equal to this. Okay, and the Mach number in here, okay, is so this is the Mach number, which is, let me say, less than 0.5 actually. Right. So all I do is just, you know, what is the big deal, you know, just slow it down to Mach 1. So we'll just pass it through a normal shock wave, go to the tables and just look at it. You know, corresponding to this, we get a ratio of the total pressures in front and behind the normal shock wave and the Mach number behind it, which is subsonic. You know, why are we going through this process? You know, is there more to it? We'll see. Okay. So that's all there is to it. So we have subsonic speed, you know, of the flow behind the shock. Okay. Okay. So now, since we're kind of assuming that there is more to it, so let's go ahead and see this. You know, let's do this for the second one, which is a combination of an oblique shock and a normal shock. Okay. Let's do that. Okay, so if I do for the second one, right, so this is the second one, right. So essentially here, so I have an oblique shock. Okay, so I do have an this is an oblique shock and this is a normal shock. Okay. So, essentially what we will therefore have, so we have, say, look, if I look at a free stream here, so if I look at this free stream here, okay, so I have this, okay, and then this free stream is deflected, right? The free stream is deflected like that, and okay, so since this has to be a normal shock wave, so what I'm going to do is do it this, keep my shock basically normal to this, okay. So what I'm going to do here is keep my shock normal to it, okay. So then here it doesn't deflect at all, it goes like that, okay. So that is essentially the so you understand, okay. Now what you have to understand, if you look at this, you'll be like, okay, both these are tilted or inclined. Well, these are inclined with respect to the horizontal, of course, these are, but whether this is an oblique shock or a normal shock is dependent how the angle it is making with the free stream. So in this case, if you look at this, this is the angle, okay. So this is the angle which is 40 degrees actually, this beta is 40 degrees which is given. So you see this is the free stream in this case, okay. This is the free stream and the shock is making an angle, okay, you know, the acute angle is 40 degrees if you look at this, okay. So this is the oblique shock, okay, and here if you look at this, this shock is actually making 90 degrees with the incoming flow. So here the flow comes, okay, so this is my incoming flow which is Mach 3, right, and then it goes and hits the okay, then it encounters this oblique shock, it is deflected, it comes here and I make it pass through another shock which is normal to it. So there is no deflection, it follows its path, but of course there will be differences in its properties. So this is the normal shock, okay. So if I do this, then okay, so basically this I'm going to just call this as P01. These are going through changes in you can consider the flow field as basically 3 regions, composed of 3 regions. So you've got this, this and this, okay. So now let us look at the oblique shock first, okay. Let us look at this first. So when I do that, okay, so how do we go about this? The first things first that we do is calculate the component which is normal to this oblique shock based on this. Now beta is given to us, right. So therefore what we calculate is Mn1, which is M1 sine beta, right. And this comes out to be 1.93, which is nearly 2, okay. So then corresponding to this Mn1, okay, corresponding to this we get a P02 by P01 to be this, okay, to be this, okay. And so there if you look at this ratios, so we had a point, you know, we had a like a 0.3, you can say 0.33 and 0.8. So P02 by P01, so P02 is 0.3 times P01, okay, and P02 here in this case is 0.8 times P01. So in this case P02 is less. So the total pressure behind the normal shock is actually less than the total pressure behind the oblique shock in this particular case, okay. And of course then we calculate the Mn2, which is again it is around 0.6, okay, and of course then we have an M1, okay. So corresponding to M1 equal to 3, corresponding to a shock wave angle of 40 degrees, we will go to the theta beta M relationship, calculate the deflection angle, right, calculate the deflection angle to be 22 degrees. So this angle here this is the deflection. So this is the deflection angle. So having done that, so we should be able to calculate the Mach number behind this oblique shock, which comes out to be okay, this is something that we have done, which comes out to be 1.9. So therefore the Mach number here is 1.9, which is nearly the which is nearly 2. Okay. So here of course it was 0.5, we directly got so I pass it through a normal shock, I directly get a subsonic flow. Here of course I haven't got a subsonic flow yet, it is still slightly supersonic. So therefore we will now pass this through this normal shock and see what we get. So we will stop here, we will continue from here next class, okay, and complete this. Okay, thank you.